Good afternoon, everyone. I'm Yipu from Tokyo University, Japan. Today, I'm honored to present our latest research titled on fabrication of multi-material structure from austenitic to ferritic stainless steel while dual arc additive manufacturing. This work is a collaborative work between Tokyo University and Tsinghua University. The outline of the presentation is generally divided into 6 parts. First, let us begin by exploring the background. As we all know, to fabricate multi-material structure, the conventional manufacturing involved multiple steps: melting, casting, shaping, finishing, and joining. Each requires substantial time, energy, and specialized equipment. From raw material to the finished component, it typically requires days to weeks to complete. In contrast, additive manufacturing streamlines production by directly converting feedstock into the nail net shape component. This approach shortens the production cycle to a matter of hours, reduce materials waste, and enhance the design flexibility. According to the American Society for Testing and Material Standard, the AM process can be classified into 7 categories. Among the typical metal AM technologies, wire arc additive manufacturing provide a combination of high deposition efficiency, lower device and material cost, and unlimited building size, making it promising for fabrication large-scale structural components. However, basic wire process usually introduce one wire into the melting pool at given time. Hence, it is inevitable to change wires frequently when fabricating multi-material structure. To address this issue, a novel dual wire arc additive manufacturing system are developed, which offer the capability of fitting 2 metal wires into the melting pool in a sequential or simultaneous way. This figure depicts different manufacturing process types of the D1 setup, including the gas tungsten arc welding, gas metal arc welding, and the plasma arc welding. Moreover, D1 process also have several extra merits, such as double deposition efficiency, refinement to the melting pool, and the most important is that the superiority in fabricating multi-material structure. Compared with conventional welding, D1 offers a promising option to optimize the bimetallic joint through compositional gradient design due to its ability to adjust individual wire feeding speed. Therefore, the objective of this work can be divided can be summarized as follows. First, to validate the feasibility of fabricating austenitic to ferritic stainless steel multi-material structure while D1 process. Second, to demonstrate the superiority of compositional gradient design in fabricating multi-material structure. And the last is to review the microstructure evolution mechanism of multi-material structure during the deposition process, inspiring the further optimization. This slide shows the experimental procedure. The figure A illustrated the schematic diagram of the D1 system. The corresponding processing parameter and the chemical composition of the two wires are listed in the table. The figure B illustrated the tensile specimen, the position of the tensile specimen extracted from the directed deposition sample and gradient deposition sample. So let's move on to the result part. The macroscopic overview, hardness profile, and the microstructural distribution of the directed deposition sample are displayed in this slide. The hardness in the interfacial region exhibits evidence enhancement compared to the austenitic standard side and ferritic standard side. To explain the interfacial hardness enhancement, the interfacial microstructure were examined using EBSD and TM. The matrix is characterized by the lazy alpha prime martensite occupied with secondary phase delta ferrite and retained gamma austenite. Therefore, the interfacial hardness enhancement can be mainly attributed to the presence of alpha prime martensite. In fact, the martensite transformation can be attributed to the interfacial remelting behavior. As the schematic diagram shows, during the deposition of the ferritic standard sphere, the unsolidified austenitic standard layer remelted as the arc passed through, enable elemental dilution at the interfacial region. To analyze the elemental dilution behavior of the interfacial region, EDS line scans were carried out layer by layer along the building direction. It can be found that the elemental concentration of the nickel reveals a stepwise decline across the interfacial region. To estimate the stability of the gamma austenite in room temperature, the martensite start temperature were calculated. It is obvious that the martensite start temperature excess room temperature across the interfacial region, indicating gamma austenite is unstable under the room temperature. The equivalent of the chromium and the nickel coordinate were also marked in the shaped diagram. The coordinate of the interfacial region is pinpointed within the austenite plus martensite plus ferrite phase area, which are coincident with the experimental observed results. In the gradient deposition sample, a more complex variation in phase fraction can be observed, particularly between the martensite and the retained gamma austenite. It has been widely reported that the ductility of the martensite standard spheres can be improved while activation of the trip effect, which relies on the introducing retained gamma austenite. Given such a unique microstructural distribution, its mechanical property and deformation behavior is highly worthy to investigation. To compare the mechanical property of the directed deposition sample and the gradient deposition sample, a series tensile tests were carried out along the horizontal and vertical direction. As a result, in vertical direction, the strength of the gradient deposition sample is similar to directed deposition sample, but the elongation are relatively lower. In horizontal direction, the gradient deposition sample exhibits significantly higher strength than directed deposition sample, which is while its elongation is relatively lower. Moreover, in situ DIC method is performed to monitor strand polarization during the tensile test. We can find that the strand concentration tends to generate from the two sides to split to the whole gauge dimension in HD, which cracks always, while the cracks always initiate at a relatively lower level of strand in HG. Both VD and VG exhibit similar deformation behavior with the higher strand zone located at the ferritic stainless steel region. Finally, the microstructural evolution mechanism are expected to be explained. However, as a general rule, the deposited layer always undergoes high frequent thermal cycle during the warm process, making the phase transformation sequence hard to figure out. To address it, a 3D finite element model was built. The thermal history was reviewed to assist the investigation on the microstructural evolution during the deposition process. To analyze the phase transformation, the phase diagram is also indispensable. The estimated parameters such as melting temperature, A1 temperature, and A3 temperature are provided by the equilibrium phase diagram. Combined with the result of the history, the microstructural evolution mechanism was systematically reviewed as shown in the schematic diagram. In summary, with the gradual reduction of gamma stabilizer element along the building direction, the retained austenite content decreased stably, whereas the delta ferrite exhibit an offside increasing trend. Notably, the volume fraction of the alpha prime martensite first increased and then declined. In conclusion, the multi-material structure from austenitic to ferritic stainless was successfully fabricated while D1 process. Due to the vegetable interfacial remelting behavior, martensite transformation tends to occur if at the interfacial region. The manipulation of retained austenite was realized by compositional gradients design, indicating further potential for structural optimization through the compositional gradient deposition. The strength of the bimetallic joint was significantly enhanced at the cost of a slight reduction in ductility. With the assistance of the temperature field simulation, the microstructural evolution mechanism was comprehensively reviewed, providing a foundation for the future optimization work. That's all. Thank you for your attention.